This is Vodcast 11A. In this video, we're going to talk all about solutions. We're going to revisit classification of matter before we define what a solution is. We're going to talk about concentration in video A and how we make a solution. In video B, we're going to save these two at the bottom, concentration or dilution calculations, as well as colligative properties. So first, how do we classify matter? This chart should look familiar to you from a previous unit. All matter can be divided up into two sections, either a mixture or a pure substance. We studied pure substances before. They are either compounds or elements from the periodic table. A compound is more than one element bonded together. In this unit, we're going to focus more on this side, and we're going to talk about mixtures. We're going to talk about heterogeneous and homogeneous mixtures, specifically solutions, which are homogeneous mixtures. Do you remember what that means? The difference between hetero and homogeneous? Is it uniform, or does it have separate layers or pieces? That would be heterogeneous. Heterogeneous. If the mixture is non-uniform, meaning it has different layers, or it has different sections, or it settles over time, the solids fall to the bottom. This is usually happening with large particles. You can also have a colloid, which does not settle over time, but it's also a heterogeneous mixture. These have smaller particles, and a colloid is something like whipped cream or shaving cream, something that's in between the phases. This unit, our focus is homogeneous mixtures. Something is homogeneous, it's uniform, it's all the same all throughout. It has the exact same composition at the top, the bottom, the middle, all over. If we would look at it under a microscope, it would always look the same. They do not settle over time. In this unit, we're going to be referring to a liquid solution, usually dissolved in water, so aqueous solutions. But a homogeneous mixture can be a gas, for example, air, or it can be a solid, like an alloy, brass or steel. You can't pick apart different pieces of air or brass or steel. It's uniform, it's homogeneous, it's all the same. Same thing with an aqueous solution. Here's a suspension with a picture. You can see down here there's some kind of solid that has settled over time. So these are large particles that will settle due to gravity. It's not a homogeneous mixture. Neither is a colloid. A colloid, again, is a mixture of two phases, two states. Like I said before, a gel or a foam, or even the clouds. So it's kind of gaseous and liquid all at the same time. Usually they're not clear. They do not settle like a solution. And we can test it with this Tyndall effect. If you use a laser beam, you can usually see the beam through the colloid, whereas in a solution, those are usually clear, so you can't see the laser beam if you shine through it. Also, colloid can be coagulated by heating it. If you think of milk, what happens to milk when it goes bad, or when you heat milk, it can kind of get clumpy. It'll pull the solids together out of the liquid. That's what coagulated means. Solutions, what we are going to study. Homogeneous mixture. Can be solid, can be liquid, can be gas. Again, we're going to focus more on the liquid. And we're going to focus on these two terms, the solvent and the solute. In a solution, the solvent does the dissolving, and the solute is the thing that is dissolved. So if we're dissolving salt in water, the solute is what's dissolved. salt, and what does the dissolving is the water. The solute particles are very, very small, and that's why our solutions are usually clear when we use water, because water as our solvent is clear. Again, using water, we can say we have an aqueous solution, aqua aqueous, because we're using water. This will be our primary focus for this whole unit. Concentration. Concentration tells us how much stuff is in what kind of volume of our solution. So it's a specific quantity of the solution. It's called molarity. It's represented with a big M, and big M molarity, or concentration, equals how many moles of solute, again if it would be salt, moles of solute, in how many liters of solution, which is primarily going to be water. So a 1.0 concentration will be a 1.0 molar solution. There will be 1 mole in 1 liter. If you study biology, you'll get to other concentrations. There's other units, parts per million, when you're talking about things, other things that are dissolved in water. And that would be grams of solute over grams of solution. But this is not our primary focus. This is the one that we need to know. How do I make a 1 molar solution of table salt? Well, step 1. You measure out 1 mole of the solid sample. For table salt, that's 58.44 grams. How do I know this? I get the mass from the periodic table. I'm going to pour it into a very special called volumetric flask. All my solids down here at the bottom, 58.44 grams. I'm going to add some water, and then you swirl to dissolve. Once all your solid is dissolved, you add water up until the 1 liter mark. This is a very specific volumetric flask. It only does 1 liter volumes. Put a stopper on it, flip it over, and invert to mix. You have exactly 1 mole in exactly 1 liter of solution, so we have a 1 molar solution. We can do a volume comparison. When you mix solutions, if you were to put the water in first to the 1 liter mark, and then you add the table salt, what would happen? The volume actually goes up. Why? Because those sodium and chlorine ions need to take up space. So they're going to dissolve in the water. The water is going to surround themselves around the sodium cations. Here's my water. Those with 2 H's. And there's going to be chlorines. And they're going to be surrounded by the hydrogens in the water. So all of this is going to take up space, so the volume increases. But on the flip side, if you add water and ethanol, remember this, the volume actually decreases. If I would add 5 milliliters of ethanol to 5 milliliters of water, you'd think you'd get 10 milliliters of solution, but it actually goes down. Why? What happens here?
Here's a cool experiment you can do to see the spaces between molecules of water. First, take an empty pop bottle and fill it with exactly 1 cup of water. Add another cup of water.
Hi, Mom.
Mark the 2-cup level with a marker. Now dump out the water.
Why do I have to do all the work around here? Here you go. You're welcome.
Now, add a cup of water to the bottle. Now drop in some food coloring so you can see it better. Get your parents to help you add 1 cup of 99% rubbing alcohol. The kind you get at the pharmacy.
See, 1 plus 1 doesn't always equal 2. There are a lot of spaces between the alcohol molecules, little pockets where the water molecules can fit. So when you mix a cup of water molecules with a cup of alcohol molecules, you don't get 2 cups of liquid.
It's a molecule thing. You can learn a lot about molecules just by mixing them together.
What do we know about water and ethanol? They both have your favorite topic in molecular forces, hydrogen bonding. So these guys are actually going to attract each other even closer, so my solution gets more dense and therefore takes up less space. Water is our common solvent. In aqueous solutions, water is always the solvent. It's the thing that does the dissolving. Because water is a polar molecule, remember our scale, something that's polar falls in between 0.5 and 2.1. Because water is polar, it can dissolve anything above 0.5. So water can dissolve polar compounds and ionic compounds. How does this happen? We say like dissolves like. Polar solvents dissolve polar or ionic solutes. If we needed to dissolve something that was non-polar, we'd have to use a non-polar solvent, something that's between 0 and 0.5. What happens? Your solute expands. Your solvent expands. When you mix them together, they can actually dissolve. But only if it's like dissolves like. Otherwise, oil and vinegar, oil and water, they separate into layers and they won't dissolve in each other. Our concentration again. We measure how many moles are in how many liters. So our equation, big M molarity or concentration equals moles of solute over liters of solution. How are we going to use this equation? Let's try some. How many grams of magnesium chloride must be added to water to make 1 liter of 1.0 molar solution? Plugging in the numbers that I know into this equation, 1.0 big M molar equals, what else do I know? 1 liter, I'm solving for X, which in this case is moles. To get moles by itself, I multiply by 1 liter on both sides, and 1 times 1 equals 1, so I need 1 mole, but the question asks me how many grams of magnesium chloride. Again, our snowman's going to come in handy. 1 mole magnesium chloride. Magnesium is a 2+, chlorine is a 1 minus MgCl2, and I need my conversion into grams. If I look up on the periodic table, the molar mass for magnesium chloride is 95.21 grams. So that's a relatively easy conversion. 1 times 95.21 grams divided by 1 is 95.21 grams of magnesium. Number 2, if 10 grams of sodium hydroxide are dissolved in enough water to make 500 milliliters of solution, what is the molarity? Here I'm solving for big M. Big M equals moles over liters, but I'm in grams. So I have to do one step first. 10 grams, sodium Na, 1 plus, hydroxide, 1 minus. I need to convert that, using my snowman, to moles. If I find the mass of sodium hydroxide on the periodic table, it's 40.00. So 10 divided by 40 to get moles will be 0.25 moles of NaOH. I put my moles back in my molarity equation, 0.25. Divide that by, my solution is 500 milliliters. In my equation I need to be in liters, so I divide by 1,000. And I get 0.5 liters. Plug this into your calculator. 0.25 divided by 0.5 equals 0.5 m, or 0.5 molar solution. And number 3, what will be the final volume? Now I'm solving for liters. I'm given my molarity. 2.5 m equals, I'm solving for liters. My solution is calcium chloride, CaCl2, and I'm given 22.20 grams. I have to convert that. 22.20 grams of calcium chloride. Looking up the mass on the periodic table of calcium chloride, at 110.98 grams. When you divide that, that comes out to be 0.2 moles. So plugging 0.2 moles into our equation, you gotta get liters into the numerator because it's in the denominator. So I multiply both sides. And to get liters by itself, I have to take 0.2 moles divided by 2.5, my concentration molarity. Entering this into your calculator, you should get 0.08 liters as your final solution. Check all of those. Make notes on where you have questions. We'll talk about these specific calculations when we come to class. We'll do more practice on the next worksheet.